Good afternoon. So our first speaker this afternoon is Professor Dmitry Kaledin from the Russian Academy of Science. He will speak about how to enhance categories and why. Thank you very much.
Thank you for the very nice presentation. Very good to be here again. And I have to start the title, which is not on the website, so we don't know what category. I'm going to make a little foundational talk, and I feel a bit justified in this because Mohammed did one yesterday. Similar. And this concerns stuff which Mohammed had for Mohammed. So kind of like the last slide, where he said, okay, now you have to work with quasicategories and what, but I don't want to go into that. So this is a talk about why maybe you can avoid going into that. Okay, but let me start forward with something familiar to set up kind of the kind of implementable explain. We all know that there are community data, community squares, they will decorated, blah, blah, blah. These days, people also often study categories, so there's a notion of community square of categories. This one is already there. Okay, let's try this one. So it's a 4. It's a race. 4. After we try to put the names to this. And one thing which is never written, but always assumed, is that unity square of h, that in fact is actually more than just a diagram. There is also an extra piece of data, which is an example of that. In principle, you can say that there are three maps in either direction chain of each other. This is also too much. Bigger than for unique, but you have a specific way to say that. And then you can also introduce a notion of, say, Cartesian or co-Cartesian square. So where are the units of? So Cartesian square is something such that it has some kind of prime, with concepts, and again, an isometry, that's there. But this we have to make it. And co-Cartesian is in the other direction. T prime. Once we have this, here, some of this, new company. And Cartesian squares are because we know some stuff. And so there's this thing we should write for product. The definition has to have papers. T0, T1. Also, we are still zero, you know. 0, T1. T1 and also begin an isometry with the images of these two guys downstairs to see. Now, for co-Cartesian square, they don't always exist. They have to go exist. But there is one example of co-Cartesian square of categories, which is very useful for one. For example, of co-Cartesian square. And it's used by so-called localization. So let me know like one, a very small case, but it just has two objects, 0, 1, and there is only one material morphism, which is another material. The here is partial set of two elements in the water, and then we have some cases with C, and we have some kind of collection of morphisms. So every morphism in C, the morphism is equivalent to giving a function of this one. One to see. So we have a collection of them. it's equivalent to saying that we have some kind of double which is just a circle. Yes. So this is just a visual viewing of a focus of this thing. And we want to declare to make all these morphisms invariant. So in terms of this propagation squares, this amount is saying that we can consider projection here. This guy is just discrete. So it's a case where it's actually just a class of discrete on all market parameters. And then we want to construct the propagation square that we do like this, and this localization. Right. So if you spell out what's the universal property for the guy, just spelling out the definition file. Then it says that if you have some function, some v, which says all maps and because that we can launch all maps, then it's practice the relation you have to impact. So you don't know. And as I said, propagation squares in general and in localizations in particular don't hold these coordinates, but there is an example where maybe let's take as C the case of a small category function. No. And W, let's take the class of the in practice, when we work with categories, we always work up on equivalence. So people don't distinguish between categories. They should, all the statements you make should be invariant on the passing equivalent case. It makes sense, but just let me work on the matters. And of course, in equivalence, if you just look at this guy, it's not important. It's only worth up to the right? So it's not important. But you can force it to be done. However, there's a very easy dilemma, which I will give the exercise, which says that in this case, localization exists. And is actually given by, so we know it's like 0, and it's like this. It's a case where you have the same modes. Okay. But more things are not found on the nodes. So they are not possible. Okay. Great. Now, as I said, in principle, we want to care about taking this up with equivalence. So we could considerably simplify our life by working entirely in this category of categories. But I want to emphasize that this particular notion of a commutative square, Cartesian square, is not visible in the level of category, nor in fact in the level of category. So remark. Let me give an interest so we know how standard commuting. The square like this is not commutative square. Because the positions here are not indicative of small, the positions here are not exactly equal, they're only not. It is a commutative square that has there. The notion of Cartesian square is different. So even if it is Cartesian in the sense, it is never Cartesian in the Eugene's historical sense in this local. It's not. And the reason for that is that if you want to construct this activation, to check this universal property, the input data should be really varying like this plus an element. And this guy depends on the choice of value. If we just come down to K0, then a commuter square is just a square, especially some going to exist, but we don't fix it. But once we don't fix it, we lose the universal properties. The situation here is similar to, say, kernels in a billion categories versus codes in the derivatives. So, first, you can construct a code by replacing a map by quite a lot of map, which is it's objective and taking the code of the map of complexes. But it will not have the same universal property. So there would be an optimization, but it's not unique. And the code, again, it's unique after an isomer, but only after the there's no current chip. So the sharing here is. And the point here is that if you just want to work with classical functors, and we want this to have reasonable properties, then this cat zero should not be treated as simply a case. It should be treated as a case with plus one. And in this case, we know very well something else. In fact, let me just go back. We know that actually two cases which are functions, but also isomorphism between them. So we know how to work with this in this point. But the reason I wanted to this example such a tail is that kind of situation is happens quite often. This is not the only example of localization where what we get as a localized category is not good enough to consider simply a category. It needs to be defined as structure. And in other situations, the set of structure is not common. So what's typical? What are typical examples of localizations in real life? We should know. Avrei sapere che sia provocante come la chance per le cose. So in general, localization is used, for example, constructing derived categories. It's probably the oldest and best known example. Where it has the complexes and the and also in some kind of more topological context, which we use data for ubiquitous when mathematics are in the world of topology. Значит, мы consider category of common text, for example, form definition is the thing of logical spaces, and the direct common data. And it's kind of accepted reason by now that what we get as localization is accepted that we get a category, but in fact we get more. It's a category to something which is roughly fitting in public health. And there are various notions in enhancement in literature which are all doing it. So one which is simple state is that so in general. Kind of the zero level requirement for this enhancement is that so localized category doesn't just have a set of maps to control. It actually has a whole homotopical type of maps, and the set of maps is just ideal. This homotopical is just a set of kind of components, but it also has some type of homotopical groups. Already for cut zero, here, what we have, I mean, here maps I think it was the function, but we know that the full structure that we have all functions and elements between them, so it's a group order. And you can look at this here, and it will be a homotopical which has pi 0 and pi 1. In this case, it doesn't go higher, but in general, we go over this, so there are all type of methods. And if you want to axiomatize such a thing, one option is to just consider a category enriched in topological space, meaning that wherever objects that have a topological space, like myself, blah, blah, blah. Очень пишется. So in general, we have in the localization situation, we have so I have a small h for just localization, what we know about that will tell you h. Let's see where which let's say about this most special. And the naive localization is recovered, so the set of maps in this case for the objects just by 0 for the space of maps between them and the start. And the problem with this is that kind of the whole idea of this localization is to throw away some irrelevant information. When you construct derived category, you want to forget that there are different resolutions for the same object. So you want to treat them all as basically one. And this works up to the point. If you look at the naive derivator, but this is constantly. Here you have slightly more than the tree. So you actually have a bonus official set of maps, which you don't want too much. And the upshot is that these things should be considered not on the nose, but again under some kind of experience. Perhaps it's easier to think about the agreement analogy. So for the right categories, for example, another of this would be a good cheat. So you have a category where the object, you have a complex of maps. But they don't care about that complex in zeros. So you introduce a notion of quasicategories between categories, and you only consider those after quasicategories. And it's the same here. So only one is very up to the. But then somehow this becomes circle. So I mean, you want to localize, and then the result is something behind that localization. But then what is localization, right? It's kind of unclear. And also it's hard to control because it becomes very complicated. So there are better models than this particular one, such as complete single space of child rest or quasicategories which we use by amongst there. And there are better models, but they're all models with different examples, so it's kind of so. And what I want to present today is a kind of alternative approach to this question. I mean, what is localized category? What is a category? Which kind of solve the problem by reducing general case to this particular case, which we know how to work. And then result is defined by the explorer controls, so you don't need to go with topology. No simplicial sets, no multi-equivalence, no monoset, nothing like that. All this gets removed from the definition. Of course, it remains as a computation tool, but it's not in the definition. And the idea of how to do this, I mean, this whole business goes back to Grothendieck, and this also goes back to Grothendieck, and it's an idea of philosophical theory. So let me give you an idea, and then let me give you a statement on what one can actually prove. Use manual simulation. here, look. Say, okay, so this is category definition for the spaces. To this unification of code. And one does it by the formal derivation. So basically there are two derivations. When we have some kind of case in recent political spaces, we don't have a single case. We actually have a lot in the following. And any small category I we look at it. We actually have a case with a function from opposite polarity. We have the function category. So this modification for functions. This is modification for I opposite. So one not only have to see, we also have a collection of these days for all time. So when we have something which for the spaces, we can take out. We can just take forever the objects instead of powerful spaces and take the usual case of the main. But we can take a allocation not only for C, but for all those guys also. We can then take the allocations. But we don't allocation by because this one is. And the question is whether so these are just ordinary. No, that's but we have possible. And the question is, can we recover kind of the whole? Not a perspective on these days. That's the question is enough. The answer is well, for some part. Okay, now let me give you some statement, which is, I mean, this is just metaphysical. Let me go back to analysis. But as always, in case of theory, let me do some packaging. Of course, I want connection with reasons, but not only that, if you have a function between for A0 and A1, there's a function between different functions. So I want to remember that. And there are some common isomorphisms when you have the position. So I want to remember this kind of structure. And it can be very nice to package. You use my real. So there is this packaging that you need to use. And this is now the data of the construction. It's actually not from 5 which is actually very old. It's the first one with J. So, what is a family of categories indexed by some? Indexed by some are. Formally, the data are So first of all, whatever is object in I allocate to AC. Whatever the morphism. Само контролляет, whatever the morphism I have. Like this. And then for controllable pair, there are some controllable pairs of morphisms. There are some identity positions of the partners, subject to some kind of constraints. And the point is that all this, which is overplayed, can be packaged into a single category in the concept. So for all this, you do it all. Because in the category, you have to objects. So consider something which can be called C, category of pairs. I C, I an object with I, C an object with C I. And then morphisms from I C to I prime, C prime, are by definition sort of where the morphism from I to R prime, and the morphism from C to the step of R C prime. And this whole additional structure can be encoded in just the fact that it's second position. And at the end of the day, what we take are a category and the function. So there is a notion of, and you can also characterize functions which appear in this construction. There is a notion of typology. And the problem is, and to do it, this one-to-one corresponds to kind of category design. So this is what we want to use because this has much less data level. And then also there is so there are for categories 5 over I. Okay. And then if you have two of them, the function between them over I. So the function between them over I is the function. Which fits in the indefinite square like this. That's a function plus minus 1. And if both are Grothendieck vibrations, so you have a correspondence between these things and data like this, then such a way defines the collection functions in the vibration. And there are some additional maps. And there are maps. Compare maps like this. And gamma scope partition. If all those things are the upshot is that you have a notion of over some critical value, and the notion of one. Okay. Now, here I said that you have, which I think forever, I think it was the contract in the area which I want to state. You don't need to consider all categories. It's sufficient to consider something smaller, and I found it convenient to restrict attention to partial sets. So you know it. Partial sets. And then for every holomorphically reached category, X, let us define a family of categories for also. Packaged into a single organization. Population. Variables. So we have a some J is this translation of the category of function on the record. Now, I'm being slightly floated here. The actual definition of this family should be more involved, which would, I mean, here I only give you the fact, right? In principle, also in transition functions, I know, but before there is a construction, you don't go in one step, but still have to say something. I'm not speaking this all of this. And then it's clear, right? So the forward. Assume we have to logically distinguish categories. Then, well, in the words, this corresponds with a fully federal engagement because that's correct. Things five by our course and identity plus particular function. But let me now this means exactly. And then a function. We there the function. So Grothendieck name, by the way, but this time it was a derivator. I'm looking for derivator. Whatever call it. I think it's associated with derivator. And then there are functions between those derivators. That's usually. Actually comes from a I think almost I have to say something, so this should be flat. Okay, the condition, which you can always achieve from the becomes whatever. Comes from that. Categories. And then two functions are isomorphic, usually in Greek. Corresponding maps are modeled.
You have an English version of this here,
There is no sense.
in the sense that complex in that sense, finds itself a complex in that sense. You form complex with calculus on. Yeah.
This can't wait. In the form of a single packaging code, yeah. There's some kind of exception. This is kind of the ground level. Corresponding maps are this is just the whole here. So what it says is that you can recover the homomorphism of these guys. Purely you can embed it effectively into basically in spite of the a posteriori, a priori it's something clear that these fibers over was actually form a well-defined category, because this force was large category. So if you have two collaborations, and there are two main, there could be two main actions. And what, so part of the point here is that for things of this form, this does not happen. And the function is defined by a station that's sufficiently large. So that's okay. And so we have well-defined thing, and then this is. Okay. So this is here in words. So you can consider this. Let's say. Let me put something here to indicate that this is not just categories because the function is actually private, so it's not a partition that we define. Then I can again localize with respect to equivalences. And this is again the same as considering identity plus the functions. And the claim is that here we have fully breaking living on the homotopical. And the fact that I can forecast here is not important because all our models now are proven to be equivalent, particularly in the so this is the this is fully breaking. So what else one can do? One can also describe the image. Check image. One can pose some conditions saying that the population satisfies these conditions, it cannot be count. Now, I don't want to actually do it because it's not that easy, but maybe 5 or 6 minutes. Similar to, say, accent, single accent for homotopical. It's not something very hard, but the point is you don't need to know what these are. I mean, accents are random. I mean, you can choose different genetic set of relations, whatever involves in this area. But you can do this. And then, so we think of vibration satisfying these types of enhancements. Crystal define and enhance consumer vibration. For X. For equipment is defined as and this is kind of so the underlying usual is the type of the guy all the time. This is thought of as an enhancement for the type of it. And then so you have now we want to take all the usual notions of the theorem, move them to the context, and for some of them this works literally. So things have explained literally. First of all, the notion of filtration. So I mean, enhanced function in fact basically the function is cartesian force, and then it's for effect on this. And second, which is actually more useful here, is the notion of agenda and agenda. So we have two categories. Then I remind you that in general, knowing that parent was in one direction, the function in the other direction. And there are two function maps between compositions and conditions. And in this case, the Jean-Pierre and functus is exactly like the and functus. They could have left, shown them in the Jean-Pierre. And it's very useful because kind of more fundamental theory in category theory is possibilities of that. This is what in practice people actually use when they construct something in the model. You construct some real functions, but then they now they're going to reduce. They don't put the construct because it's unique. So the uniqueness of a junction, there is no word. But now let me discuss something which I think is instructive, and this is what happens to partition web. I mean, examples, I mean, general theory, but also there are standard constructions which are used for localization. For example, the localization in the direct taking for then localization model categories. And for all those situations, it's very easy to show directly that's very clear over in so that's satisfied. So everything that which should be an example is an example. I mean, this is not well, there's actually more. So there's a proposition. And it says that, well, I'm kind of deliberately misleading here. I'm not saying whether the categories are small or not. This category force is large itself, so the C can never be smaller than the result. But we can have small. So small half category is not smaller. And in this case, it's equivalent to saying that this is then, so for categories which are not small, especially more difficult, we actually have to do some kind of traceability here, for example, access to global storage, so I don't want to do that. That is attention to now small areas in this sense. And then it turns out that actually any small category can appear as an organization of especially the partial research. So it fits into local region. Or following flow. So if I have some J, then I have J, I mean J is a category, but if it's powerful category, then it's here, okay? And then it's basically the same accreditation picture, but now I do it in the decimal complicated. It's like minus 3. It's not really difficult thing, conventional, because we know that you can replace it with very narrow, and then you have to work a little bit, but not that much, so that you not kind of approximately very much of the set. Not very far. But it has good power, so every C has this presentation, but then of course J is part of force, so we also have the function. So that's what can be said, but let's look at parolas. And then parola number 1. We've got answer to the question before raised, which said that what we call the image of this guy needs some work. What we call that page. Categories, small categories, and not the boss. Then let's go on and get into Cartesian code. That means that there is an internal form with respect to Cartesian code. So there are specific functions between anything that can take this CNC prime, subject to universal property, which can be necessary something else. And then there's corollary number 2. Chemistry. So I think that will be excellent will be the kind of category, but let me say the following. So definition. A square, commuted square of some category in time functions. Semi-Cartesian. If so when you have a square like this, can be complicated. You have a player output from C01 to this fiber flow. And if a third Cartesian, one be different. So I'm not going to do that. I want to say that this is, I don't know what it's kind of term, but I call it an equivalence. And to me, this means that this is essentially subjective and slurred. Like in simple words, what happens is that this have the same as plus object, so every object here, you need an object here, you need the up and horizontal. But there's not nothing. Now, you can take just categories and functions you want to zero C and take just this type of work. But at least typically is not an category. It's usually not good. Some legend very up. What? So you can have, you quite often can have a Cartesian square. And there is a lemma which says that whatever the zeros you want, we have semi-Cartesian square. And then, moreover, it's actually corollary with population here. Second corollary is that such semi-Cartesian squares actually have one more, which is weird. So corollary such we have universal properties. name it. So we have. And then if you have some kind of community square, then there exists optimization. And the only difference with the non-hand situation is that this thing is unique after non-unique. Non-unique. And it's actually quite a direct analogy. So what you do, you look at this guy, you present in this form, take this J, and then we evaluate the center of this square at this J, and this J. So basically, we do it with that property. Once you have this representability. So what happens is that we cannot have even squares, but we can have semi-even squares. And there are sufficient tutorials so we can look at that. And this is very easy because as I explained in the beginning, if you just look in the real square concept, they don't have so this work as homotopical square and homotopical, or main concepts they're going to use. And those cannot be in general described in your proposals. They have to be imposed as a method stuff. But on this set, this interplay between looking at these things that get localized or looking at them as particular things that get the type of overpass, you get this. And then in practice, you can do this to bootstrap all theories. So you need to construct, for example, you need to group two categories, or you can do. And the result is unique after an equivalent, which is unique after non-unique. That's where, and this non-unique is crucial because this is actually where all the entire kind of problem bootstrap. Okay, so this is the basic shape of the thing, and then there are also products you can do. For example, you can get the notion of you get enhancement for a specific enhanced category, again for free. Basically, it's like this. So what's you need some kind of enhancement. That's the workforce. Right? So what? So it's viable. Some J is what? Well, it's a function from J to the category, but you can package it by development construction. You can just vibrations over J, which I can do. The vibration from usual stuff, so that's difficult. And there are compares out there, and there are also way change for connection, blah blah blah, and the rest is very much forward. And you can develop the whole theory. So I give you the main things where you actually need to go into presenting objects, some kind of comparison with homological categories. But after this, the rest of the story can be developed as a category theory effect. You don't need to do. You don't need to mention the official set, for example. I mean, the sole goes into this. The rest can be developed now. Model variant. Okay, I think I finished more or less here, but one last thing I should say is the start of the whole list. So this is just a comment. So I've been raising this up for some